Welcome to the lecture 30 of Physics 10 in 30 lectures, the last one in the series. We wrap up this semester with remaining particle physics material, concluding with a conceptual overview of the standard model of particle physics. Since we are wrapping up Unit 4, we start with a section of Unit 4 essay questions, which might be relevant in preparing for the essay timed assessment in this unit. Then we continue the earlier discussion in particle physics with the introduction of the Yukawa Meson, the particle hypothesized to mediate the strong nuclear interaction. We call this meson now pion. This discussion highlights the power of dimensional analysis, especially as we navigate the unfamiliar territories in physics. After a brief mention of muons, not the actual Yukawa meson, but mistaken for it initially due to its much heavier mass compared to the electron, the original particle in the lepton family, and pions, actual Yukawa's meson, participating in the strong interaction. After this, we wrap up this lecture with an overview of the standard model of particle physics, with a separate discussion of modern tweaks. Thank you so much for following our course content for the semester over the 30 lecture sets, adding up to more than 52 hours. I hope some of you will consider calculus-based physics for scientists and engineers, which is covered by the 3-semester sequence of Physics 4A, 4B, and 4C. Thank you. Okay, so this is the last of the essay assignments, kind of overview or I don't know, me just reading things out loud. This is for Unit 4. Again, I'm doing this because it might be relevant for those of you attempting essay timed assessment. And these are the assignments that we used to have that we don't have anymore. And after this semester, I'll probably be deleting these out of the Canvas shell entirely. Right now, it's not published. So I want you people to have a chance at kind of seeing the questions, and these questions are being multimedia oriented questions. I will also play some of these videos, again, sound muted and just skipping for the details. If you're interested, you can find these videos on YouTube. So the essay assignment for chapter 12, quantum mechanics, there's this kind of introductory material. Let me not read it out loud in the interest of time. You can read it for yourself if you're interested. Let me play these videos that illustrate these quantum mechanical phenomena, and I'll read the question and the model answer in the peer grading assignments again. We don't have anymore. So let me first play these 2 video clips again in bits and pieces with the sound muted, closed caption on, so that you can kind of get a sense of what they are. This is a photoelectric effect demonstration from National STEM Center. I think it might be a British organization. Yeah, it's UK. Oh, by the way, this is the video that I used to use for my, I guess, Physics 4C. And for the lecture videos, I've had to kind of replace it with another video that had a less of licensing restriction. So yeah, let me skip ahead. So I think, yeah, you can see that when it charges up the plate, that electroscope, it's being obscured a little bit by closed caption, but you can see that being, I think right now he charged it by what's called charging via induction. If you're interested in the details of the technique, again, you can watch the full video. And this time he's gonna do it with a regular lamp and nothing will happen. Yeah, it's a pretty bright lamp, but nothing happens. And then I think he replaces that with a UV lamp, and then now you see it discharging. Yeah, and I don't know if he will do the charging it positively portion. He might not be doing that. Charging it positively is a little bit harder because you kind of have to know kind of the pairs of materials that'll result in a positive charge versus a negative charge. I never memorize it, so I think that's the kind of thing older scientists pay more attention to. Again, if you're interested in, it's not a long video, it's only like 3 minutes. You are welcome to find it on YouTube on your own and watch it. Let me play the second video again with the sound muted, close the captions on, and just the bits and pieces. So it's going to be talking about wave-particle duality. I assume that involves de Broglie wavelength, probably. Oh, let me make sure the closed caption is on. Yeah, these videos are long, but I'm glad they're still, online. Wave particle duality, part 1 from Bosman Science. So I think he does a kind of review of particles and waves. Yeah. He's using PHYS simulation for waves, by the way. And yeah, this is him just kind of flow chart slash diagramming, describing these things. Yeah. And you see, yeah, and then he's describing a double slit experiment. If you think of those coming in things as particles, then there should be no interference pattern. Yeah, like depending on like what kind of accuracy you expect, they might overlap, but it would be just that. Yeah, now when it's waves, that's where you get interesting features. I'm surprised he didn't use. He might be actually using video from the simulation. These features look kind of like that simulation. He might be doing a kind of cropped version of that. And yeah, there is kind of destructive and constructive interference resulting in these alternating fringes. That's a typical wave feature. And now what it's describing here is that wave particle duality, which is that with the electrons, you can observe that wave-like behavior instead of a particle-like behavior. Does it mention de Broglie wavelength? And this happens, by the way, when you fire one electron at a time. You do need to gather enough statistics, but really what happens is a single electron wave function interferes with itself. It's not like two separate electrons interfering with each other. That actually doesn't work for a number of reasons. If you try to observe it, then you end up kind of disturbing the wave functions enough that they will look like the interference fringes will get washed out, and what you see ends up looking more like particles again. That's actually the kind of I guess we didn't spend a lot of time on it with the Schrodinger's cat. That kind of goes to how observation, the act of observing always has to involve some sort of interaction with the thing we are observing, and it'll result in some amount of disruption. So yeah, again, this is a 6-minute video. If you're interested in the full detail, you're welcome to go find the video on YouTube and watch it yourself. I've given you all the details so that you can do that. Let me stop this here. Okay. All right, so those are the two videos. Let me bring up my PR grading assignment, and then I'll read you through the question and the model answers. So this is the PR grading assignment that has the model answers. Let me read the question. Let me read the question. The first video shows a demonstration of a photoelectric effect, which shows ultraviolet light has enough energy to free electrons from a zinc metal surface, but visible light does not. Explain how this demonstrates the relationship between photon energy and frequency given in section, it says section 13.2. In our version of the textbook, it'll be section 12.3. So given in section 12.3, the photoelectric effect given in your textbook. Explain any new quantities or physical constants in your answer. And let me read the model answer. Following are some important ideas in the explanation of photoelectric effect. A. Light behaves like a particle in interacting with the electrons and transfers energy to the electrons through collision. B. If a single collision does not give an electron enough energy to escape the conductor, then electron loses any extra energy it gains quickly. That is, an electron cannot escape the conductor through multiple collisions with the light particles. With these ideas in mind, what the demonstration shows is light particles, photons, of light with a high frequency. Ultraviolet light has higher frequency than visible light, has enough energy to eject the electrons, but the photons of light with a low frequency do not have enough energy. This relationship is expressed quantitatively as energy of photon is equal to h times f, where h is a Planck's constant, new constant defined in quantum mechanics, and f is the frequency of light. Okay, let me go to question 2. Wave-particle duality is one of the more difficult modern physics concepts to fully grasp. Ever had that annoying friend who would answer a question like, do you want waves or particles? With a yes? But a good place to start gaining understanding is by pointing out key experimental features which illustrate particular aspects. In electron double-slit interference experiment described in the second video, name at least one feature of the experiment that highlighted electrons' wave aspect, and name at least one feature of the experiment that highlighted electrons' continuing particle aspect. Give brief explanations for the features. let me get to the model answers here. It's a little bit long. Here are the lists of wave-like properties and particle-like properties. First, the wave-like properties with explanations. Diffraction, the spreading of the wave after passing through the slit. Waves bend around obstacles, but particles could also change trajectory after bouncing from walls of slits. Interference, alternating bright and dark fringes due to constructive and destructive interference between two slits. Waves follow superposition principle, making in particular destructive interference possible. Particles do not cancel each other out. Wavelength, as illustrated in the interference phenomenon. Unless something has a wave-like property, you can't talk about its wavelength. The distance between bright and dark interference fringes are related to the electron wavelength, which is related to its momentum through de Broglie relation. Lambda wavelength is equal to h, Planck's constant, divided by p, momentum. Now, the particle-like properties with explanations. They are electrons. From the time of its discovery, it had every indication of being a particle. For example, having a definite charge-to-mass ratio. It's hard to see how this property would fit with a wave model of electron. How they are detected. Each time an electron is detected, the detector registers it in one location, not smeared out as a spread out wave would be. How they are detected. Part 2. Not only is the electron detected as a particle at the screen, but if additional detectors are placed to measure electron position while the electron is moving from the slit to the screen, it is still detected as a particle. In this case also, in the middle of its trajectory, not just at the end point. It is not easy to give a clear explanation of wave-particle duality without either oversimplifying it or making a statement that may need to be substantially corrected later. Here's one reasonably simple statement that has stood the test of time. Everything travels as a wave and interacts as a particle. This more or less matches our description of matter waves, and it also holds for photons. Every time low-intensity electromagnetic radiation is detected, they are detected one photon at a time. The traveling as wave part accounts for interference in both cases. Okay, so that's quantum mechanics, chapter 12. Let me get to special relativity. Okay, here's the essay assignment for chapter 13, special relativity. And again, there's this kind of long thing here. In the interest of time, I won't read it out loud. I encourage you to, I don't know, pause this video and read it. I think I actually did a version of this in the recorded lectures. So, but you know, if you want to read it, you can always pause the video and read that part. So there are these 3 videos. Let me just play them briefly. I'm gonna again play them on mute and kind of skip around. Let's see here, Einstein and the special theory of relativity. Yeah, this is a minute physics video. I think I used to use quite a few videos from them. So again, Einstein and the special theory of relativity by Minute Physics. So it's yeah, a minute and about, you know, under 2 minutes. So so I guess the main point is I think he's going to talk about the postulates of special relativity. So I'll just skip it through, you know. Yeah, about the light, and then there's a postulate of well, he's still on the first postulate, that principle of relativity. And this is the thing that he introduces that I think is visually good, this whole rotating axis. That kind of an aspect of the space-time diagram that I do lecture on. So you will see that here. And yeah, the rotating time, there will be more about that in the second video. So let me get to that again, kind of skipping through. So okay, so this is the second video, the twins paradox primer, rotating time, by the same channel, Minute Physics. And this is a little bit longer, just under 3 minutes. Again, if you're interested in the whole thing, you can watch it. And he's kind of going through this. I'll kind of spend a little more time when we get to rotating axis thing. Yeah, so this is more of a like a geometric rotation. That's an analogy that you can draw to trying to understand space-time diagram. Yeah, so that's the rotating axis, and this is a kind of way to visually illustrate how simultaneity is relative. That 1 person 3 seconds is not that. It's yeah. So okay, yeah, relativity and simultaneity that showed up briefly, and the way you explain twins paradox is there. Oh, there's complete solution in the third video. So we'll get to that. Here's the third video. Complete solution to the twins paradox. It's a little over 3 minutes by the same channel, Minute Physics. And he did the setup in the previous video. And the paradox is that that as the twin travels, both the twins, I think the other one is getting older slower. So the traveling twin is actually younger when they come back. So if in what perspective, at what moment in time, from the traveling twin's perspective, did the Earth twin get older? And this kind of rotating axis explains that through the shift of the sense of simultaneity. This jump can happen basically instantaneously. So let me kind of skip through the rest again. If you're interested in the whole video, you can go to YouTube and watch it yourself. Yeah, that's the solution. If you don't want to make it kinked, you can make it gradual. It's still the same thing. This kind of shift of simultaneity will happen much more quickly than, yeah. So, yeah, Lorentz transformation is what it is. I think the lecture actually does mention it. We don't spend a lot of time in it because, ours is conceptual physics, not mathematical physics. So yeah, those are the videos. Let me read the questions and the model answers. Let me get the model answers on the side as I read the questions. So question 1. Give a description of the twins paradox. What is the setup and which aspect of the setup is considered paradoxical by those who don't understand special relativity? If you feel adventurous, try giving a resolution of the twins paradox in your own words. And here's the model answer to that question. This is the paradox in the twins paradox. From the perspective of one of the twins, the other twin is the one moving. That is, for the twin on Earth, it's the twin who is traveling that is moving, and for the twin who is traveling, it is the Earth twin that is moving. And since the motion is relative, there is no such thing as absolute rest. And you can't say that it's the Earth twin that's actually at rest. Whether something is moving or not depends on the perspective, or reference frame of the observer. Time dilation says moving clocks run slow. So in the Earth twin's view, the traveling twin's clock is running slower, and the traveling twin is aging slower. But in the traveling twin's view, the Earth twin's clock is running slower, and the Earth twin is aging slower. So who's right? When they get back together, who should be older? The resolution of the paradox, which is explained in the video, is that the situation is not completely symmetric. The velocity of the Earth twin is not changing, but the velocity of the traveling twin changes as they turn around for the return trip. This makes the Earth twin's perspective more correct in some sense, and the traveling twin is actually younger, aged slower. The video does a better job of explanation, although it is quite a bit mathematical. Let me read question number 2. The premise of the original Planet of the Apes, the book, there's a link to Wikipedia, I think, is that the astronauts are able to be personally present on the Earth centuries later because they traveled to Betelgeuse, or Betelgeuse, a star 430 light years away at a relativistic speed, and also returning at a relativistic speed, they aged much slower than the rest of the Earthlings, who would have been about 900 years old if they survived. Describe a conversation that might take place between the astronauts and the Earthlings on their trip to Betelgeuse. I guess I'll say that Betelgeuse, and on their trip back. For the simplicity of a plot, assume existence of a magical communication device. Call it an Ansible. It's a device that pops up in science fiction here and there, which allows for an instantaneous, i.e. simultaneous, communication regardless of distance. Let me read the model answer here, a bit long. If the astronauts are traveling toward the Betelgeuse at 99.9% of speed of light, their Lorentz factor will be about 22, meaning the distance of 430 light years will be length contracted in the astronaut frame to only about 20 light years, and they can make the journey in their lifetime if they start young. As the astronauts travel toward the Betelgeuse in their 20-year mission, if they remain in contact with the Earth through Ansible, they will find that the time passes more slowly on Earth. Earth clock, from their perspective, is time dilated by a factor of 22. So as 20 years pass on the spaceship, they will see only about 1 year pass on Earth. So the conversations would involve change of season and holiday celebrations, but depending on the year, they wouldn't hear about presidential elections. When they come to a stop at Betelgeuse, that's when suddenly, from the astronaut's perspective, about 430 years of time passes for Earth. And depending on when the apes take over the Earth, the astronauts can no longer contact Earth, and they certainly wouldn't care about who the next president was, given that everyone they knew would be dead now. When they decide to come home, The moment they reach their cruising velocity, 99.9% of speed of light, coming back home, is when another 430 years of time has passed for Earth. And this time, the apes will definitely be rolling the Earth, and the astronauts can give their ape future colleagues a 1 year head up on their arrival. Most science fiction authors don't get this right. Even Orson Scott Card, who tried to make Ender's Game as hard science fiction as possible, got this aspect of relativistic communication wrong when he describes Ender and Valentine's relativistic journeys. Yeah, and in year 2026, when I'm recording this, I think I can say that I still haven't seen a single science fiction story that gets all these relativistic business correct. Even the Hail Mary project, which got some of the details right, got other details about how, let's say, an alien culture who developed interstellar travel without learning about special relativity, what kind of mistakes they would have made. That's described incorrectly in the book. I haven't watched the movie yet, so I don't know the movie, but in the book, that aspect is not described quite correctly. Okay, let me go to the last chapter and the last of this essay assignment. That would be chapter 14, nuclear and particle physics. Yeah, there's a lot that I wish we could cover that we don't. Let's see, there's part 1 radiation and part 2 neutrinos. Oh, there's a lot of videos. All right, so this is what I'm gonna do. I'm gonna just check to make sure that all these videos are still up. I don't know if I actually remember all these. And I'll just flip through. I guess this is from TED Ed channel. Is Radiation Dangerous? By Matt Anticoli? I don't know. You can look it up on YouTube. This is about a 5-minute long video, and I guess he's probably talking about a biological effect of ionizing radiation. Non-ionizing radiation, not so dangerous. Ionizing radiation, yes. I think that banana might be about background radiation from radioactive potassium. So if you're interested in the whole video, you can go to the TED Ed channel and find this video from 10 years ago. They're all kind of old because, I found these videos back in, I think, 2018 when I was first putting these together, maybe 2017. Let me go through the second video, Radiation in Everyday Lives. This is from channel Ian Mead, Radiation in Everyday Lives. It's a 3-minute long video. Is there a closed caption? Maybe. Yeah. Smoke detectors. There's americium in there. It's an alpha source. Yeah. Beta. I guess. Yeah. So this is kind of things that we cover in the lecture now. Alpha, beta, and gamma. Positron emission. Yeah. Beta plus. I guess. Yeah. And then there should be. I guess that's. Yeah. I think that was the gamma radiation. Using gamma radiation to sterilize. Yeah. Gamma rays. Yeah. Anyways, so if you're interested in the 3-minute or so video, please go watch it. Let's see, lest I leave you with only positive impressions of radiation, including below video as part of. So this is about the Chernobyl, one of the biggest nuclear disasters that happened, I guess, in Ukraine, as part of the former Soviet Union. So yeah, it's at the channel PHYS News, inside the cleanup of Chernobyl, the world's worst nuclear disaster. Oh yeah, there was an HBO series. Was that series that long ago? Huh. That makes me feel old. Let me turn on the So again, the whole 7.5-minute video, you can go to the channel and watch it. I think this is more of a human interest story than physics. But so I'll kind of flip through. There's enough detail here that you can find the video and watch it yourself if you're interested. And from 8 years ago, it's still up. So yeah. Yeah, I thought most of that stuff was safe now, or not. I don't know. With some of the nuclear waste, it depends on the half-life. Like sites of American nuclear bombing, Hiroshima and Nagasaki, those are, I think, completely safe now because all the fallout products, their half-lives are short enough that they are all decayed away. But with the nuclear reactors, there might be some of the fission products that it's present that wouldn't have been present in a nuclear bomb. So, anyways. So those are the 3 videos for part 1. I guess let me read the question and the answers for part 1 first, and then I'll do part 2. This is the nuclear physics part, basically. So here are the answers. So question 1. How is nuclear radiation, aside from nuclear power generation or nuclear weapons, used in modern everyday life? Give 2 examples, preferably modern devices, not radium clocks. And for each example, explain in some detail what important role nuclear radiation serves in the functioning of the modern device. Note, for a technical reason, X-ray does not qualify as nuclear radiation. X-ray device is an example of radiation producing machine, but it does not use radioactivity. I do cover that in the lecture now. Let me read the answer. Excluding nuclear fission, power generation, nuclear weapons, and X-ray imaging, following are some examples of uses of nuclear radiation in everyday life. First, from the textbook section. So in our textbook, this would be section 14.7, medical imaging and diagnostics. 1. Radiopharmaceuticals, where a radioactive nuclide in a compound is used to tag the molecule for tracking as it moves through the body. Because the radiation emitted by the radioactive nuclide can be detected with the detectors placed outside the body. 2. As an example of radiopharmaceutical, use of radioactive iodine to image the thyroid. I think somewhere here. Number 3, as another example of radiopharmaceutical, use of radioactive thallium in thallium chloride salt to image the cardiovascular system. And 4, positron emission tomography, PET, which uses beta plus emitters. And from one of the videos, number 5, smoke detectors. You wouldn't have to list so many. Number 5, smoke detectors, using americium-241 for ionizing air, which then can be used to detect for presence of smoke particles. And number 6, radiotherapy, used in cancer treatment. Gamma rays used to selectively kill cancer cells. Video also mentions PET scan, which is not repeated in this list. It was already in the textbook's list. There are also other uses of radiation that you may have found in your own research, such as radiation-powered exit light. I think I mentioned it in the lecture as a tritium-based source. In the old days, radium was used for similar purpose, but as dangers of radiation were better understood, these uses have stopped. Read more about radium girls. There's a Wikipedia page. I also mentioned it in the lecture. Radioactivity, of course, is more widely used in research setting. I did not include any of them in the list above, but peer graders may use their judgment on whether research setting uses qualify as modern everyday life. Okay, question number 2. Why is nuclear radiation and ionizing radiation more broadly, like including X-rays, dangerous? Explain the biological reason for the dangers of nuclear radiation and what precautions may be taken for those who need to work with or in proximity to nuclear radiation. Okay, here's the model answer, number 2. That's a long answer. Ionizing radiation and all nuclear radiation is ionizing radiation, although some ionizing radiation is not nuclear radiation. It's dangerous because particles in ionizing radiation, whether it's a helium-4 nucleus, electron, or photon, alpha, beta, and gamma rays, have enough energy to remove electrons from atoms and molecules, ionizing them. Once ionized, these ions can undergo energetic chemical reactions, and if these happen inside our body, these chemical reactions can damage DNA and other cell structure. The precautions that may be taken can be memorized with the mnemonic time, distance, and shielding. And I now have the radiation safety lecture. Time means to limit the length of time of exposure to ionizing radiation, since the total dose received is product of rate of exposure determined by reactivity level of radioactive sample and other factors, and duration of exposure. Distance means to establish a safe distance. Many ionizing radiations follow inverse square law rule, meaning if you increase your working distance from the source by a factor of 2, your exposure rate decreases by a factor of 4. Shielding reminds that some ionizing radiation can be shielded with the material placed between the radioactive source and you. Alpha particles can be most easily shielded. A few centimeters of air will do. Beta particles can also be relatively easily shielded. A thin metal plate will do. Higher energy beta particles require more care to avoid secondary radiation. Gamma rays are like X-rays and require thick layers of lead shielding for substantial reduction of exposure rate. The order they are listed here are, by the way, the recommended order of priority. First, limit how long you must be exposed to ionizing radiation. But if you must be exposed, then do it at the farthest distance you can be exposed while still doing what needs to be done. And if neither is possible, then try blocking the radiation with a shielding. But shielding is the least effective method of protecting yourself, and it is only a method of last resort when neither time nor distance are practical. Okay, let's go to part 2 about neutrinos. I think there's only one question, but 2 videos. The first video might be from Mediate Physics, or not, never mind. So it's a neutrinos and the solar neutrino problem. I do briefly mention that in the lectures somewhere. It's at the channel Antonella Massini. That's whose channel it is. Let me play it with the closed captions on. And this 5 minute, a little under 6 minute video. Gonna again skip through. She will talk about neutrinos, what they are. They go through almost everything. There's a lot coming from the sun. It's an elementary particle. I did do an intro to neutrinos, I think as part of the lecture 29. Yeah, so there's all that. This is, I think these are screen grabs from Wikipedia. So yeah, so you can, if you're interested in the details, you can go to her channel and watch it. I'm just gonna skip through. So I think she's talking about neutrinos from fusion. So there's some number of neutrinos we should be receiving from the sun. When the scientists try to detect it, they found only about a third of the neutrinos expected, and that's a problem because either it means our model of the sun is wrong, or something else. And is that resonance? Maybe. Oh no, I think she's illustrating beat phenomena. The neutrino oscillation is kind of like a beat. So yeah, again, if you're interested in the whole video, you can go to our channel and watch it. And so this is kind of the at length description of neutrinos. And let me look at the second video. It's been a while since I've seen it, so I'm not quite sure what it covers. So this is Why Neutrinos Matter by Sylvia Bravo Gallert. It's at the TED Ed channel. You can go look it up if you're interested in the whole video. Let me make sure the closed captions are on, and I'll just flip through. Yeah, lots of neutrinos. I think they are both covering basically the same thing. I want you to just give two perspective. One with a kind of a bigger production budget, and one from a smaller creator. Yeah, that picture is just so wrong. Like, in vacuum of space, there's no cosmic ray shower. You need, atmosphere for that to get started. I guess they are calling neutrinos a ghost particle. Ice Cube is one of the, I think they're still ongoing. They have detectors in the either Arctic or Antarctic, I forget which. They have detectors buried deep underground. I think they use the scintillation in ice to detect the neutrinos. So yeah, you can again watch it, the full little less than 5 minute video on your own if you're interested. I'm just gonna skip through quickly in the interest of time and for copyright reasons. Let me read the question number 3, and I will read the model answer out loud. So question number 3. Briefly explain what neutrinos are and give some examples of important roles neutrinos play in modern physics research, explaining their roles in your own words. For the purpose of modern physics research, you may cite recent discoveries made with or made regarding neutrinos. So the solar neutrino problem, that's now like 20 plus years ago. Let's say that's modern enough for us. So here's the answer to question number 3. Neutrinos are electrically neutral particles that are in other ways similar to electron. In technical terms, neutrinos are leptons. They are special in how infrequently they interact with other matter, because they don't interact by strong nuclear force or by electromagnetic force, only interacting by weak nuclear force and presumably gravitational force. Neutrinos have been used to verify standard models of solar dynamics. Neutrinos are produced in fusion reactions within the sun, and neutrino oscillation, proposed and verified in connection with solar neutrino problem, has provided greater insight into elementary particles. Astrophysicists think they can use neutrinos detected from elsewhere in the universe to gain an understanding of cosmology, other than some observations of neutrino bursts from supernovas. Like from a single supernova, they would detect like a few dozen neutrinos. There's more coming from them, but what we are able to detect are a few dozen. Other than these, I think these are still research to be completed, if ever. I haven't looked it up in a long time, so some of that research might have been done. Although I guess gravitational wave probably got more attention in recent years. I'm not an astrophysicist, so I don't keep up regularly unless I remind myself. So those are all the essay questions. Again, I'm reading this out loud because those of you who are doing essay timed assessment, you might see these questions or related questions. So these are the essay questions from chapters 12, 13, and 14, covering quantum mechanics, special relativity, and nuclear and particle physics. And I guess this is the last of these videos. So thank you for watching. Bye. this is what your textbook starts chapter 11 with, but I think now is the appropriate time for us to address this now. So it comes down to the question of the types of elementary interaction. And I know when I teach physics 4A, I tell you about all these contact forces. Turns out none of those contact forces are elementary interaction. And up until this point in your physics education, we have only dealt with the two elementary interactions, gravity and electromagnetic. All the kinds of contact interaction at the very elementary level, they are electromagnetic interaction. Electromagnetic interaction between atoms in my hand and the atoms here. So when we were looking at the atomic nucleus earlier, that was the first indication that this might not be all the interaction that's out there that can explain our universe. Because when you look at this atomic nucleus, it cannot exist if this is all there is, right? So you might look at, okay, so beta decay, that's a nuclear interaction, and that it involves some kind of interaction that doesn't involve electromagnetic force, because this neutrino is electrically neutral, so it probably couldn't have anything to do with the electromagnetic interaction. But when you look at these types of beta decay type of interaction carefully, it turns out that the properties of beta decay, it doesn't really fit in. So there's some kind of new interaction that's involved here. But it's not the new interaction that would explain this. Here's one reason that I can tell you actually. So this kind of new interaction, it involves the new particle neutrino, right? And what's the one defining characteristic of a neutrino?
Electrically neutral.
Okay, that's one. How did we infer that it's electrically neutral?
Conservation of charge.
Okay, I guess you could do it that way. Okay, so why couldn't there be two neutrinos? That's one positive, one negative. So there was one other experimental fact that we had to fit that made us infer that it's electrically neutral. What was that experimental fact? We don't detect it. That it is virtually undetectable. So the fact that it's virtually undetectable also kind of excludes this as participating in whatever interaction this is. Because if there's one thing you can say about this nuclear interaction, is that it's a very strong interaction. Whatever it is, it must overcome electrostatic repulsion between protons. So this is a very strong interaction. And if this neutrino participated in that strong interaction, then we would have detected it, electrically neutral or not, because it would have interacted with the other atomic nuclei around it, and we would have somehow seen it. And not by electromagnetic interaction, but by that other type of strong interaction. So whatever interaction this neutrino participates in, it's not the strong interaction that you see here. So the interaction that neutrino participates in, it's apparently yet another type of interaction that's not involved in holding up the nuclei together. So we give it another name. It's called, I guess, I don't know when particle physicists became more creative, but this name must have been given before they became more creative, because the name they gave to this interaction was, any guesses? Well, this is what they called it. They called it weak interaction. So the theory of beta decay, which if you want to look up the names, the people who came up with the theory of beta decay were Pauli, as I mentioned. He's the guy who suggested the neutrino. But actually the name neutrino wasn't from Pauli. He wanted to call it neutron before we had a neutron. So the name neutrino comes from a guy named Enrico Fermi. He's an Italian physicist. I think he came to US during World War, or around World War II. So in US, there's a national lab called the Fermi Lab. Guess who that's named after? Enrico Fermi is the one who came up with a theory of beta decay that correctly predicted some of the decay rates.
And that is the theory of weak interaction. And the picture that I'm presenting here is not actually the full theory of interaction. You saw in the little diagram, you saw there were two mediator bosons for the weak interaction, W boson and Z boson. They are apparently not drawn here. So the correct version of the Feynman diagram for weak interaction actually looks like this. Neutron turns into proton, emitting a virtual boson, virtual, I guess, W minus boson, and this decays into electron and neutrino. So that's what the full picture is. Let's not get into that right now. So this is a new type of interaction, but it's entirely separate from the interaction that's holding the nucleus together. So, which means there's yet another fourth interaction. It's kind of, so with the particle physics, this is going to be a common theme. You start out with a relatively simple description that you thought was the complete description of your universe. Then you have this odd little thing where you have to start introducing new things, and then it explodes into a whole thing. I guess with the forces, we are lucky that the fourth one that we introduced, we think that's the last one. And no one's suggesting any new interactions. And that fourth interaction, we call it strong interaction or strong force. Once again, I suspect these names were given before particle physicists became more creative with their names. So what I want to use the rest of the time today is the early descriptions of this strong interaction. And this is where we pick up description of something that's referred to as Yukawa's meson. I guess this is probably the only place where I can mention the idea of Yukawa potential or Yukawa type potential. So this is the kind of starting place. You start by thinking about what is the requirement on this new type of interaction that we know nothing about. So imagine you are a nuclear physicist in the 30s, 40s. You know enough about electromagnetic interaction, and you know enough about gravity that in the particle interaction you can kind of ignore gravity. It's kind of spectator in most interactions. So you know enough about electromagnetic interaction, and you know enough about quantum mechanics to know that the quantum mechanics and the theory of magnetism has been fully validated in the study of atomic spectra, right? So in the description of the Bohr model, which matches experiment very well, we didn't have to introduce anything new. So that's your starting place. And now you are trying to introduce a new interaction, which must explain this new phenomena. And a type of correspondence principle continues to hold. It's this idea that this new thing that you are introducing must not mess up the old thing. Right? So based on that, you can start to kind of put some constraints on how this strong force should behave. And I guess in the interest of time, I'll give you the one biggest characteristic of this strong force. The biggest characteristic of this strong force is that this must be a short-range force. Why? So let me tell you what I mean by short range. How does gravitational and electromagnetic forces depend as a function of distance? 1/r², the inverse square law, right? These two forces, their forces go as 1/r², or if you look at the potential, their potential goes as 1/r. And it turns out this type of dependence characterizes a long-range interaction. You can kind of see it. You know, what are the type of structures that are held together by gravitational force? Planet, anything bigger? Solar system, anything bigger? galaxies. I'm not sure about the universe, but there are like clusters of galaxies, and there are superclusters of galaxies. So gravitationally bounded systems, there's no limit to how large a scale it can be. So, so it comes down to when you do detailed scattering calculation, the scattering cross-section for this type of potential ends up being infinite. There's, however far away you get, you are always affected to some degree. And so electromagnetic forces are also has an infinite range, but the reason we don't see the effect of electromagnetic force in the large scale is reason that there's positive and negative charge. So anything that has a net charge kind of attracts other charge. So the planets are electrically neutral more or less. That's why you don't see it on astronomical scale. So these are the long-range forces. So when we call this interaction short range, that means we are limiting it to, somehow this has a different distance dependence than this. And so I just want to make sure that you have some intuition for why we are assuming strong interaction must be short range. Like, why?
When I touch the table, I don't come inside the table.
Okay, so you don't see. So you don't see this strong attractive force in the macroscopic scale. All right, so then let's go down to microscopic scale. What kind of range should this have? What's the upper limit on how far away this force can be effective? So you're saying it would not be effective within a millimeter or micron range. I think you can go a lot smaller.
The size of the atom?
Okay, so size of the atom, yeah. So size of atom is about scale of 10 to minus 10 meters, right, an angstrom. Does this strong interaction play any role, any measurable role at 10 to minus 10 meters? Oh, well, that's size of nucleus. This is size of an atom. Two different things. It doesn't suck the electron, but I guess the electron actually turns out it doesn't participate in strong interaction. So, maybe. So biggest evidence you can cite to argue that at this atomic scale, strong interaction is negligible is that it's the atomic spectra. When you look at the spectrum of a hydrogen atom, it's completely explained by just the electromagnetic interaction. So if this was some important player, then you wouldn't, that would not be the case. So this is actually still long range because interaction at this range is still only mediated by electromagnetic interaction. So, okay, so let's just be more specific. We know the typical size of nucleus. Typical size of nucleus is about 10 to minus 14 meters, about 10,000 times smaller than size of an atom, and maybe 10 to minus 15. Do I want to call it 10? Let's stick with the 10 to minus 14. So this is short range. The range of this nuclear force must be about 10 to minus 14 meters. And so Yukawa is the guy who proposed what kind of form this potential can take in order to limit this interaction into this range. And what he guessed was, well, let's hypothesize this potential over this form. So instead of a potential function simply going as 1 over r, he was adding a multiplicative factor to this, or multiplying another factor to it. And the factor he added was the exponential decay. So he was hypothesizing that the potential that can be associated with this might take this form. E to the minus distance over some characteristic length. And based on this experimental observation of the nucleus size, what he would guess is, well, or I guess at the time it would be more like upper limit on the nuclear size. He could guess, well, this characteristic length, maybe it's about 10 to minus 14 meters. And is it kind of intuitively obvious that if the potential is modified by multiplying by this, that would limit the range of your potential? Yes, kind of enough, right? Yes, yeah. I guess we can just leave that there, and that this is the characteristic length that determines how quickly this exponential is decaying. And here's the actually exciting thing. Once you have guessed this much, then there's a method with which you can guess the parameters of the particle that must be mediating this interaction. So we said in the earlier discussion that comes from quantum mechanics that electromagnetic interaction is mediated by a photon, right? So, in quantum mechanics, everything that's a field has a particle associated with it. Everything that's a particle has a wave associated with it. So you can go back and forth. So if you have a strong interaction and there's some kind of field, some kind of influence of force, then there would be a force mediator associated with that interaction. So Yukawa's guess for what that mediating particle is what came to be known as Yukawa's meson. And what I'm telling you is that there is a technique for calculating or estimating the mass of this meson. So, and the technique is, I think this is kind of difficult to emphasize enough, especially in the first 2 semesters of physics, is dimensional analysis. So when you go back and look at the older physics lectures, you might feel like your physics instructors are overemphasizing units. And that's, I understand that perception, and I would blame that perception on the fact that you haven't seen how powerful a technique dimensional analysis can be. Looking at units, it's not all that powerful when you feel like you know all the physics there is to know. You simply calculate the numbers, you're done. You derive the formula, you're done. You don't need to look at the units. Looking at the units becomes useful when you actually don't know that much physics. Here, this strong interaction, I know nothing about it. There's no formula that tells me what it is. Somebody guessed this, so I have this characteristic length, but beyond that, I still know nothing about it. I don't know, is there a charge? But what I can do is, I can guess a mass scale that's associated with this length scale. And I can make that association based on the dimensional analysis technique. So let me, it won't take long, so let me just sketch out the consideration we are going through, and let's just do the dimensional analysis and kind of come up with some formula for this mass. So, all right. So for this dimensional analysis, the starting place is this. I have this length scale. So the quantity I'm trying to figure out is the mass of this meson. Sorry, I introduced a new word without defining it. For now, let me call this Yukawa's particle. So I have this new particle, and I want to know the mass of the particle. So all right, I have this mass. And the very first step in dimensional analysis is first guessing what parameters might go into determining this mass. So let me give you a starting point. One of the parameters I think needs to go into determining this is the characteristic length, right? I mean, that's gotta be one of the inputs. But if I just end here, then I'm kind of screwed because length is not mass. So I need some additional parameters that's going to help make me sense of things here. Any guesses for additional parameters? Physical constants. What physical constants do you think should matter here?
Electric constant?
Now, electric constant probably won't, because whatever this is, it's not electromagnetic interaction. So if we are thinking of like epsilon naught, that's definitely not one of the parameters because it's not an electromagnetic interaction.
The speed of light?
Why speed of light? Because it's not electromagnetic. So there must be some other reason for speed of light to be important.
Like special relativity?
Yeah, in the end, it's about special relativity. And once you are dealing with the nuclear physics, energy scales are such that relativity matters. Whenever relativity matters, speed of light, it's not the light that's important. It's that this is the universal speed limit. So whenever relativity becomes important, this plays a role, whether it's electromagnetic or not. All right, so that's one more parameter. I don't think that still helps me. This is length, meters per second. I need some way to bring in kilogram, and neither of these have kilogram in it. Any other parameters? Physical constant that might play a role? What physical constants have you seen in this class?
Elementary charge.
Once again, not electromagnetic. Huh? Yeah, Planck's constant. And in fact, so this is a quantum mechanical phenomenon. Whenever you have something that's quantum mechanical, it must involve Planck's constant. If it doesn't involve Planck's constant, then there must be some classical approximation of it. There is no classical approximation of nuclear interaction, so there has to be Planck's constant, and I'm going to write down the reduced version just for fun. I don't know if that'll actually give me better numbers, but I'm just going to do that. So that's Planck's constant, and actually this is probably a good chance for me to mention these three fundamental constants that's involved in whatever happens to the universe. The three fundamental constants are these: gravitational constant, speed of light, and Planck's constant. And actually there are things you can do by combining these three fundamental constants. Those are called the Planck scale, and you can have fun with those, but we won't get to that today. For today, so whatever this Yukawa's particle is, it must involve the length scale, must involve relativity, must involve quantum mechanics. And let's see if that's enough to give us a unit of kilogram or unit of mass. So, all right, let's see how they combine. So once you determine all the parameters that must go into determining this quantity, then what you have to do is now, how can I combine these in such a way to yield the correct unit? You can think of this as a way of eliminating all the wrong answers. Because, like, why am I calling it that way? Like, how are you eliminating all the wrong answers when you combine them in a way to give you a correct unit? So this is how you have used dimensional analysis so far. You have calculated some algebraic answer on an exam or homework, and you are told to check units. Why are you checking units?
Because if units is wrong, then it's absolutely wrong.
Yeah, there's no way. If one quantity on one side is meters per second and the other quantity is hertz, then there's no way these two can be equal to each other. You must have made an algebra mistake somewhere, right? So this is the argument behind this dimensional analysis. Whichever way of combining these quantities there are, if they are combined in such a way that it doesn't give me kilogram, then that particular combination simply cannot be right. So we ruled that out, that particular combination. So by combining them into a form that will only give me correct unit, I'm pre-ruling out all the other algebraic combination of these that simply cannot be right. Now, if you do this correctly, there will be only one unique combination that will give you a correct unit. If there are too many parameters here, then you might have to deal with multiple possibilities. Here, I know what I'm doing, so I picked the exactly correct number of parameters to give me the exact one unique combination that will give me one unique expression for math. So let's try that. So first thing I need to do is I need to write down the units of each of these. So the Planck's constant, in SI units, it comes in the units of joule times a second. And joule is unit of energy, or if I write this all out, it's a kilogram times joule. It's energy, so it's a meter squared per second squared. The way I remember it is work done is force times distance. So Newton times meter. Newton is mass times acceleration, or kilogram times meter per second squared. So kilogram times, so Newton times meter, so meter squared per second squared times a second. And let me write it down in a way most people who do dimensional analysis do. I don't want to be really tied to SI unit. Unit is more fundamental than SI unit system, the unit of mass, length, and time. So I'm going to use the letters mass, length, and time. So what this is unit of mass times length squared divided by time, or time raised to the power of -1. Yep. I think the other two are easier. Speed of light, that's meters per second, or length times time raised to power of -1. And finally, the length scale, well, I guess it is length scale, so it must have unit of length. Yeah? So these are the units. And this is the kind of hypothesis or working setup with the dimensional analysis. Your working guess or starting point is that whatever this mass is, I want to be able to express it as an algebraic combination of these three quantities, or h bar raised to power of alpha, speed of light raised to power of beta, and the length scale raised to power of gamma. Or if you choose to look at simply the unit quantities, then what you're saying is, well, unit of the left-hand side mass is equal to the unit of this raised to power of alpha. Or so this ml squared times to -1 raised to power alpha times speed of light, length and inverse time raised to power of beta times length scale L raised to power of gamma. And the unit on the left-hand side is, I guess, to be explicit, really what it is, mass raised to power of 1. So let me actually write it all out completely. It's m mass raised to power of 1, length raised to power of 0, time raised to power of 0. Yep. So I will tell you that there is a systematic way to figure out these powers alpha, beta, and gamma. I will tell you my method for guessing and checking. So this is what I see. H bar is special in that that's the only parameter that has quantity of mass in it. So if I get this power alpha wrong, to get the correct power of n, I'm kind of done. There's nothing I can do to fix it. So I must get this alpha correct to get this correct power. So that means there's nothing else alpha can be. Alpha must be 1. Right? Okay. So once I nailed it down, then I use the other two constants to fix the rest of units. I must somehow cancel out this length and time in the remaining thing. And how you do this guess and check will depend on the setup you have. That's why I was first telling you that there's a systematic way. If you don't feel comfortable guessing and checking, you can just do the systematic way. But the way I'm guessing and checking is I look at one parameter, which is in terms of one unit only, which means I don't really have to worry about the length unit. Whatever I come up with the length, just to be for this parameter, I can use this to fix my remainder of length unit. So really all I want to worry about right now with C is the unit of time. I just want to make sure I cancel out unit of time. So as I look at that, what I see is, so this beta must be -1. So that the t to -1 gets canceled out here. All right, so this is -1. Now that doesn't give me correct length unit because I have L to the 2 and then -1 from here. So I still have 1 power of L left. So I would use this lambda to fix that. So this must be -1. So this kind of guessing and checking is a lot quicker than systematic method in most cases. So that's what I'm doing. So with this as a guide, what we would now guess is that this mass, whatever mass of Yukawa's particle is, this is the only combination that gives you the correct unit. The mass must be a combination of h bar raised to power 1 divided by speed of light times this length scale. And this somehow must give you correct unit. So let's plug in the numbers and see what kind of number we get. H bar divided by speed of light times, length scale I have to enter, 10 to -14 meters. Let's see. Wolfram alpha is usually smart enough to offer me all the correct units. So okay, I get 20 MeV, but I think this is actually enough to show you one thing. So it's heavier than electron, right? Definitely heavier than electron. It's, like 40 times the mass of the electron, but it's lighter than proton. Proton is, 2,000 times the mass of electron. So it's somewhere in between. And that's where the name Meson comes from. It's called Yukawa's Meson because it's the mid-weight particle. Its weight is in the middle between the baryons and the leptons. So now the 20 MeV, that's not really the correct number. So the number that Yukawa used must have been 10 to minus 15 for the nuclear scale. So let me just go back and fix that. And we'll just have the correct number for the next part of the discussion. So I'm obviously simplifying some things, but the core of the argument is still the same. That if you have the particular length scale, which would give you a short range interaction, then the particle that can be associated with this length scale is very likely to have this level of mass scale. And you can kind of see one thing actually. So if you have a long range interaction, like if this was infinity, then what would the mass of this particle, mediator particle, be? Like imagine your length scale that I enter up here is very, very large, like 1 meters. Very, very small mass, right? Does that match what we know about the photon? Massless. Yeah. So the fact that photon is massless is closely associated with the fact that electromagnetic force is a long-range force, or it exactly behaves Coulomb's law, the inverse square law. So anyway, so this was Yukawa's prediction that if you have a particle that's mediating this short-range force, then the mass of the particle, just a rough guess, is going to be 200 MeV per c squared. So that's one of the characteristics of Yukawa's Meson. And it's a bona fide prediction because he's hypothesizing existence of a particle with a mass that doesn't match any of the known particles. So people are looking for this Meson. So let me just quickly tell you the context where people were looking for this Meson. The context where people were looking for the Meson is in the cosmic rays. Do you guys remember a brief discussion of cosmic ray when we were doing special relativity? No? Yes, no? What are cosmic rays made of? Like what did I think I gave you a short description of what cosmic rays were. Does anyone remember?
High energy particle.
Yeah, high energy particle from the universe. So what cosmic rays are? High energy, mostly protons, coming from extra Earth, probably extra solar, possibly extra galactic sources. So let me just show you what's called a picture or artist rendering of what's called a cosmic ray shower. So air shower. Let me. So it's just a rendering to illustrate what's involved in cosmic rays. I guess I don't know how well you can kind of see it. So what I've been calling high energy proton, that's the primary cosmic ray. So this is the initial proton that's impacting our upper atmosphere. And it really doesn't matter what it is. It doesn't matter that it's a baryon, so that it undergoes a strong interaction. So in this interaction point, what it does is because it's so energetic, it produces many different particles. And some of those particles are other nuclei that gets produced, and some of the particles are what's called pion that we'll talk about really quickly, and some of the I guess that's it. So these pions are what's called the secondary rays. And these secondary rays are composed of, so pions are unstable particles. These unstable particles will quickly decay into additional particles. Pion, pi plus, it should decay into neutrino and muon. So this muon is, I think we've mentioned the muon, right? So this muon is the tertiary cosmic ray particle. You started at the primary high energy proton that produced some very short-lived pion, and then that short-lived pion decaying produced the muon, which is also not that long-lived. It lives for like 2 microseconds. But when people detect cosmic rays on the ground level here, what they are looking for and what they are detecting are these muons. Okay? So, so before the invention of particle accelerators, this was the only source of unstable particles that don't just exist lying around. They all have really short lifetime scales. This, let's see, I don't know if I remember all the numbers. So muon lives for about 2 times 10 to minus 6 seconds. Oh, this is what the booklet is for. I can look up. So I do know for a fact that the charged pions live for a shorter length of time. So let me just look it up. So pi, lepton summary, Meson, quarks. Okay, I'm almost there. Pion is at the beginning of the Meson table. So pi plus, mean life is 10 to minus 8 seconds. And that's actually super long. So this lives for about 10 to minus 8 seconds. And I say that's super long because these neutral pions, they actually decay more quickly. They live for about 10 to minus 10 seconds. So these pions and the muons are the first of the previously unknown new particles to be detected. And to wrap up this story of Yukawa's meson, I will tell you that the very first of these 2 common cosmic ray particles to be detected is actually the muon. So this muon used to go by the name mu meson, because when people did the experiment with with that cloud chamber picture with the positron, when they look, so I think its mass is like 106. Let me look up just to be sure. When they measure the mass of the muon, the mass was 105.7. So the mass of the muon was about 105.7 MeV over c squared. So when people first discovered the muon, they were excited. This is a new particle. We haven't seen it before. And its mass is right in the range that Yukawa predicted for this new particle, which is necessary to mediate the nuclear interaction. But that excitement was short-lived because when you look at the details of how muon behaves, it doesn't behave anything like this strong interaction force mediator should. For one, it doesn't seem to be interacting via strong force. It goes through materials more easily than electron does. In fact, the muon, as people studied it more and more, kind of behaves like an unstable, heavier version of electron. So today, we identify muon as the second lepton. So it's the mu meson, that's the old name. So people don't call that mu meson anymore because it's very confusing. Meson is a different category of particle than lepton and baryon. So we now call it simply muon, and that's the name you have seen when we do special relativity. And what this is a second lepton. And what you will begin to see is that the name lepton and baryon become misnomers pretty quickly, because some of the things that we call lepton are actually heavier than proton. But the lepton and baryon, their classification really has more to do with different types of forces interactions they participate in. So muon, the way you should think of it is it's like an electron in almost every sense. except it's heavier and it's unstable. And it's like electron in the sense there's a neutrino that's associated with muon. That's what this neutrino here is. This is not an electron neutrino, that's a muon neutrino. So it's in a dotted line because you don't really see it, but you assume their existence based on how muon goes. So it took people a little bit longer, a few more years, until they actually detected this pion, which was harder to detect because it's a shorter lived. And so people had to go up higher up in the mountains to see particle tracks that they could identify as, oh, that's not muon. It doesn't look like a muon track. It's a pion track. And when you look at the mass of the pion, let me look it up to be sure again. So the mass of the pion is, so the neutral version and the charged version, they have slightly different masses. I will give you the mass for the charged pion. So mass of the charged pion, pi plus minus, they are particle, antiparticle of each other. The mass of the pion is about 139.6 MeV per c squared. So this is still in the correct range for Yukawa's meson. And this is now confirmed as Yukawa's meson. So the early model of nuclear interaction, the strong force, is to treat interaction between neutrons and protons. So interaction between neutrons and protons as being mediated by exchange of pions. So, I guess, exchange of pions. So if you're trying to, I guess it has to be neutral pion by exchange of pions. So if you're drawing Feynman diagram, it might look something like this. So how the nucleus is bound together, you might think of it as, well, I have a neutron coming in, I have a neutron going out, proton coming in, proton going out, and the way this interaction is mediated is by the neutral pion. Now, this is the early model. All these three particles are composite particles made up of what we now call quarks. So in the quark model, it becomes, so there's even more fundamental underlying picture, but this is a kind of starting place. And once you kind of think of it this way, you can have more fun with it. You can because you know there are three different types of pions, right? Or I just told you there are three different types of pions. And so when you draw the diagram this way, the only way you can draw it is with a neutral pion to conserve charge here. But that's actually not the only way you can draw it. You can actually draw it this way. You can have this neutron going to proton, and this proton going to this neutron. Then what you would say is the neutron, well, to turn into proton, you must emit pi plus. So that, and this pi plus getting, pi minus. You must emit pi minus. So that you have neutral particle coming in, positive and negative particle going out, so the charge is conserved. So this pi minus getting absorbed by this turns proton into neutron. So this is the early model of a strong interaction. And what we'll go over on Tuesday next week is the standard model as it stands today with the discretion of quark model. But I have to do a little bit of an introduction to where a quark model comes from. And that takes another 3 hours. Well, not 3 hours, but including that takes another 3 hours. So for the 1 hour lecture today, I'm just wrapping up particle physics, and I really wanted to give you an overview of the standard model. And for the first overview, I will tell you that I had to specifically go find the version of this poster that's out of date. So the most up-to-date version kind of includes some complications that I would rather introduce under modern tweaks. So I want to first give you the overall basic features and overall structure first. And that's easier with the this older edition. I think this one was probably produced in 2012 or something. So this is the poster that I think that is exactly this poster. Yeah, so that is this poster. If you've looked at it and you've seen this. So this is the kind of overview of the standard model, what we know about particles. There are elementary fermions, elementary bosons. They also go by the name of force carriers. So these are the particles that we know about. And these particles participate in these four fundamental interactions. Gravitational force, which we don't really deal with in particle physics. Weak electromagnetic force, which we know the best about. And the new things that we are talking about in the last couple of weeks, the weak and strong nuclear forces. And in the standard model, one of the big features of what makes the standard model is what's called electroweak unification. So here under bosons, it actually, even the older version puts it under unified electroweak bosons. And so photon is grouped together with the W boson and the Z boson. And I guess this work was done in the 1980s, I think. So I think I told some of you that there have been no new discoveries in physics for the last 30 years or 40 years. That's what I'm referring to. This big structural foundation of what we still call cutting edge particle physics was all settled in the 1980s. Possibly before I was born. So that's the standard model. And now there were some unverified features that's in the updated version that we'll talk about in about 20, 30 minutes. And I guess, so this is the good kind of, good poster to look at, and we'll zoom into some different sections of it to just highlight the things that we've been talking about, the things we hopefully begin to feel familiar with. And we'll spend a little more time actually looking at the properties of these things. So these are probably the particles that you are, well, okay, probable is not a good word. So in terms of your level of familiarity before this class, there aren't that many particles here that you would be familiar with already. So there's the electron, that hopefully you feel familiar with. And you actually have to scroll down here for proton and neutron for familiar particles. But those are not elementary particles in our description of particle physics. So we have to start out with here, as unfamiliar as you are. Even quarks, so I guess what you ought to feel more familiar with is the up and down quarks. If only nothing else, because these make up the particles that you are familiar with, protons and neutrons. So these are the 12 elementary fermions, not counting their antiparticles. So we talked about the concept of antiparticles. They are covered matter and antimatter. So for every particle type, there's a corresponding antiparticle type denoting a bar, blah, blah, blah. Particle and antiparticle have identical mass and spin, but opposite charges. Some electrically neutral bosons are their own antiparticles. Okay? That's a good short summary of what antiparticles are. So in most of these charts, antiparticles are not explicitly listed. So here we have 12 elementary fermion, matter fermions. So for every one of these, you should imagine there's an antiparticle. There's a positron, there's antimuon, antitauon, and there's antineutrino for each one of those. So there are 6 elementary quarks that we know of, corresponding to 1 to 3 generations or families. And for each one of those, there are antiparticles. So there's 24 elementary fermions. Good. So some of the, I guess this is good time to kind of look at their properties in a little bit more detail. So we've been looking at their charge, or we know their charge already. We introduced the fractional charge of the quark and how that came to be deduced, even though we've never seen a quark. And you've been told some of the masses already. You know that electron is about half MeV. So this is in GeV per c squared. So this is the digit for MeV. So electron is about half MeV. Good. You know muon is about 100 MeV. Good. So one other feature I should point out is tau lepton, or tau is 1.7, 1.8, almost 2 GeV. It's almost twice as heavy as the proton. So lepton is more of a historical name now. Lepton, it used to mean that it's light, but today what defines a lepton isn't that it's light, because if that were the case, then tau, quote unquote, lepton couldn't be a lepton. The really defining feature of a lepton has to do with the interaction. So when you look at the interaction, so this is the second row is the particles experiencing these 4 types of interactions. When you look under strong interaction, only quarks and gluons participate in the strong interaction. Leptons do not participate in strong interaction. Lepton has no color charge, so does not participate in strong interaction. So that's what defines a lepton. So even though the tau lepton is actually heavier than heavier than the first 2 generations of quarks, or it's heavier than many of the baryons, it's still a lepton because it does not experience strong nuclear force. Okay. Quarks, so we spent a lot of time last time talking about the kind of guess at the strange quark, sometime talking about the discovery of the charm quark, and I glossed over when bottom and the top quark were discovered and confirmed. I think I looked up the dates. Top quark was finally produced in 1995 or something. But people kind of knew top quark had to exist before that. Once they believed in the quark model, and once they found the upsilon meson, which is the bound state of bottom quark, then it's a matter of, it's like, if you believe in the periodic table of elements, then the undiscovered elements, you believe they exist, even though people haven't actually found them yet. Of these quarks, I will describe to you one odd feature. It's the masses of the quarks. So you've been told this fact or statement. You've been told that proton is made up of 2 up quarks and a down quark. And you've been told that neutron is made up of 1 up quark and 2 down quarks. Okay? What's the mass of proton approximately?
1 GeV.
Yeah, about 1 GeV, right? Per c squared, if you're being, if you're being consistent with the units. And neutron is also about 1 GeV per c squared. Now, I invite you to look at the mass of the up and down quarks. Those are in units of GeV. Does this look like about 3 times up and down quarks? No, right? So I guess this is what so these numbers are hinting at a physics underneath that we didn't spend any time on. And that physics it's hinting at is that these up and down quarks inside the proton, they are relativistic. So most of the mass of the proton is not in the rest energy of the up and down quarks. It's in the total energy of up and down quarks. And really the more faithful model of the proton and neutron is that they are not just made up of these 3 quarks. These are sometimes called valence quarks or valence quark content. So this is the net quark content of proton. Really a better way to think about proton is it's made up of up and anti-up, down and anti-down. And these are kind of spontaneously produced in the kind of complicated strong interaction that these quarks are undergoing. This is part of particle physics that people have yet to figure out because So, but all these quark and antiquarks, they cancel each other out when you're adding up for net quark content. And what remains is this valence quark content. But really a more truthful representation of proton is that it's made up of a lot of indeterminate number of quarks and antiquarks. But when you add them all up, you have net of 2 up quarks and 1 down quark. Okay? And same for the neutron. So that's what those mass numbers are kind of hinting at, that if you're simply glancing at the chart, you could easily forget. These heavier quarks are actually easier to deal with in the quantum mechanical model of the nucleus, or the model of baryons and mesons, because they become heavy enough that you can use non-relativistic quantum mechanics, or not the quantum field theory. So like the bound states of bottom quark are more easily dealt with than bound states of up and down quark. So one more trivia. So when we say fermion, we do mean spin half particles. So spin 1 half, 3 halves, 5 halves. But as far as we know, all the elementary fermions have spin 1 half. We don't know of any elementary spin 3 half fermion. At least not in the standard model. I guess I don't know enough particle physics theory to know if there are any supersymmetric partners that's a spin 3 halves. But all the known elementary fermions are spin half. All right, so that's probably enough of the fermions. Okay, and we'll talk about the bosons. Those are the force mediators. They are the force carriers, and they have integral spin 0, 1, 2. And I think actually we have an elementary particle for each one of those. So let's see, you guys know about photon. It's spin 1. We talked about W boson, right? It's also spin 1. And I guess for whatever reason on this table, at least here, they are listing all the particles, both the particle and antiparticle, because the charged W bosons are antiparticle of each other, and photon is its own antiparticle. 2 photons can annihilate each other. And the neutral G boson is also its own antiparticle. Gluon, for whatever reason, they decided to list only 1 instead of the 8 different kinds that we were talking about last time. I don't know if they mentioned that, that there are supposed to be 8 different color charge. If you do go into particle physics theory, it is important how many different kinds of gluons there are, or how many different color charges there are. Oh, I said that we have spin 0, spin 1, and spin 2. So spin 0, that's one of the modern twigs. They found the Higgs boson, and Higgs boson is a spin 0 particle. Spin 2, I think most people believe in this. Most people believe that there is some kind of quantum mechanical theory of gravity. We don't have one that works yet, but we believe it exists. And in the quantum mechanical theory of gravity, there ought to be a graviton. And that graviton, based on the symmetry that's associated with the general relativity, the only gravitational wave that can be produced is what's called quadrupole radiation, not dipole radiation. And that quadrupole radiation has to be associated with the spin 2 particle. So, that's the elementary spin 2 particle that almost everyone believes they exist. So I'm going to pretend that it does exist. So those are the bosons. I guess I should point out one interesting thing that you see here that I kind of mentioned last time is just how heavy the weak force mediators are. Both the W and the Z boson, they are 80 GeV, 90 GeV, 90 times the mass of the proton. And that heavy mass is important in introducing one interesting question, and two, explaining one interesting feature that I'm going to point to that's in this part of the poster in a little bit. One interesting question it raises is that when people start talking about the unified electroweak theory. So this is what unified theory means. It's kind of saying that when you are grouping these particles together, you are saying that they are brothers and sisters. They are comparable to each other. And you can especially see that here with up and down quarks. They are comparable to each other. In fact, you have interactions that turns up quark into down quark. So they are in some sense interchangeable, like a spin up electron in a magnetic field is interchangeable with a spin down electron. There are processes that will turn one into the other, right? So if you are starting to say that these are siblings, it's like looking at one person who's 7 foot tall, another person who's 4 foot tall, and they tell you they are brother and sister. It's like, how can you be? Don't you guys have the same genes? Why is one person so much taller than the other one? So here the particle physics question is, why are these so much heavier than the other? And the explanation for that is in what's called the Higgs mechanism. And that's where Higgs boson comes from. It's something called spontaneous symmetry breaking. So in the kind of, like a Pangea theory of particle physics, the very original picture is that they are comparable to each other. They are all massless. But there's a mechanism that broke that symmetry and gave these particles mass. And the kind of mathematical procedure that does that says that there should be another kind of elementary excitation that should look like a particle, and that is Higgs boson. Higgs boson, that's the theory that was proposed in the 1980s. That's the theory of unified electroweak interaction, and that's the kind of the last structural piece in the standard model, and that's the theory that was developed in the 1980s. And I will tell you that, Higgs boson was confirmed to exist in 2014. It would have been a bigger news if they never found the Higgs boson with the upgraded LHC. Like if they never found it, that would have been actually bigger news. Kind of more of a trickling news, but that would have been a bigger surprise to particle physicists than the fact that they found it. They've been expecting it for 30, 40 years. So of course they found it. So that's one interesting question raised by the heavy mass of the W and the Z boson. And that question is now answered in the affirmative in the discovery of the Higgs boson. I'll show you in the updated thing. And the other question that haven't quite been raised because we haven't talked about particle physics yet. It comes down to when you do actual quantitative things with particle physics. So I guess I can actually use this diagram here. So I've been drawing Feynman diagrams. That's kind of a version of this, right? Two particles coming in, or particle, antiparticle coming in, annihilating, producing a photon, that decaying into other things. You've seen those diagrams, right? And when you draw it as a Feynman diagram, with each of the vertexes, you associate a coupling constant or coupling strength. How strong is this interaction? And when it's an electromagnetic vertex, like with a photon, you associate a factor. When it's a weak vertex, like with a Z boson, or with the beta decay, with the W boson, then you associate a different factor with it. When it's a strong interaction with the gluons, then you associate a different factor here. And so this is the calculation that's actually done by particle physics graduate students with the help of the Feynman diagram. That's what the tool, the Feynman diagram is for. And when you look at that coupling constant, the fundamental coupling constant. Let's say electromagnetic coupling constant, you just set that at 1. It's actually 1 over 137, but let's just set it at 1 for now. Then the coupling constant for weak interaction, it's actually comparable to the electromagnetic interaction. It's not that very different. And in fact, it's this coupling constant that hints at the fact that electromagnetic interaction might be the same as the weak interaction, or that they are in the same family. But then the thing you have to explain is why in real life is the weak interaction so much weaker? And that's explained by the heavier mass of the W boson and the Z boson. So the heavier mass does two things. One, it makes the interaction short range. Because of the Yukawa type potential, there's an exponential decay that's associated with this mass. So that means at any appreciable length scale, that's what this is describing. At any appreciable length scale, like 10 to minus 18 meters, which is only like, 1,000 times smaller than scale of nucleus. That times 30, it becomes a much weaker interaction. So this is the question, that these are similar, but these are not. And that question is answered by the heavy mass of the force carriers in the weak interaction. And strong interaction is, I guess I'm not really ready to get into it, so let's not. In lieu of going into strong interaction and color charge and all that stuff, let me just talk about the hadrons, or the joule of particles that we mentioned before. They are in this chart of in this chart of standard model also, pions. That was the original Yukawa's Meson. So originally, we thought of nuclear force as being mediated by pion, and that's not, entirely crazy model, but that's not the elementary interaction. The elementary interaction is mediated by gluons. So pion, K meson. I guess we haven't talked about rho. I don't know why it's in this list. One thing, I guess it's different. It's a spin 1. So you can kind of look at it this way, maybe. When you look at pion and rho, they are very similar, right? They both have the same quark content. So they have the same charge. Quark content determines what electric charge they can have. But they have two key differences. Rho is heavier, and it has a different spin. It's spin 1 instead of spin 0. So it's a sort of question of what gives. And this was the original evidence for what we now call color charge. It actually brings us back to Pauli exclusion principle. Where does Pauli exclusion principle come from?
Exchange symmetry.
Exchange symmetry, right? So I already said up and down are kind of similar to each other. So let's treat these two as indistinguishable particles for now. So pion is a particle made up of two indistinguishable particles. If I deal with the neutral pion, that's actually true. Here, you kind of imagine that it's true. Then when you exchange these two particles, the wave function you get has to be antisymmetric, which means they kind of have to be in a what's called a spin singlet configuration. Because, okay, so I can't test you on this, because when we did this in the lab, I told you I won't test you on it, so I won't test you on this. But in the lab, what you saw was when you have a combination of spin up and spin down, two spin half particles that are combined in this way. So this is particle 1, 2, 1, 2. When they're combined in this way, this is what's known as triplet configuration. And the reason it's called a triplet is because this is a spin 1 state, as you saw in the lab. But I won't test you on this on the exam because I can't. Once it's a spin 1, then it has 3 different projections. 1, 0, minus 1. That's why it's called a triplet. This is a symmetric configuration. The antisymmetric configuration is given by this one that you guys guessed that in the lab. So the same state, instead of plus, it's minus, and then down and up. So this is known as the singlet configuration because it's a spin 0 combination. So zero spin, there's no projection, there is really only one state. Okay? So that's why pi meson is in spin zero state, and it all makes sense. Which means, what's up with this? What's up with the rho meson? I mean, everything is same. Are we suddenly saying that, spin statistics theorem is invalid, that fermions can be in symmetric configuration instead of anti-symmetric configuration? So whenever you come across this kind of crossroad in, I guess, fundamental science, you usually have two options. One is that whatever rule or law that you believed in before is wrong. Maybe there's something wrong with the spin statistics theorem, which means there's something wrong with the quantum field theory, and that's just invalid. That's one option. And the other option is there's something you miss. There's a particle, there's a parameter that you didn't know about before. And I will tell you, every time this decision has come so far, the correct answer has been there's something we missed. This was true with the neutrino, because the option there was, well, maybe energy conservation is wrong, but the option that we missed the particle turned out to be correct. And in this case, it turns out the correct choice was that we missed something, and that's the quantum number that's associated with the color charge. So with this additional quantum number, so overall even order symmetry, it's a multiplicative symmetry. So up to what you are seeing here, up to spin that you see here, this is in a symmetric configuration, but you can put the color charge in such a way that this is in a anti-symmetric configuration with respect to color charge. So you have an additional degree of freedom. Then everything, spin statistics theorem is fine, and this is still in an anti-symmetric overall configuration. So maybe that's why this is listed there. Anyway, so there's that meson. I guess we haven't talked about any of these, but these are some of the mesons dealing with the bottom and the charm quark. And there's a meson dealing with, I guess actually that's it. There are no known mesons that have the top quark in it. Top quark is so heavy and unstable that we don't know of any bound states involving top quark. All right, so those are the mesons. Once again, the top two are what you have seen and you may be tested on, but I'm not going to test you on the rest of them because there's just so many. And the focus on physics is never memorization. That's why you get only one index card. These are baryons, and there's a very nice distinction between baryons and mesons. And this is kind of why baryon number is conserved, meson number is not. There's no such thing as meson number conservation. And when you go back and look at the meson, you can kind of see why. It has a quark and anti-quark. So when you look at the net number of quarks, mesons will always have net zero quark. So that's why meson number is not conserved. You can produce a pion out of vacuum. I mean, you still need a charge. So you can produce a neutral pion out of vacuum just with the photons. Baryons are made up of quarks, no anti-quark. Or they are made up of net quark. So if it's anything like this, any anti-quark that's there is paired up with a quark. So it's a net 3 quarks. So that's the proton that you know and are familiar with. There's the neutron. Now you can produce anti-baryons. They have anti-quarks in it, 3 anti-quarks, and everything is reversed except for the mass and I guess spin. You can't really reverse spin. This is magnitude. Let's see. So every time you see a baryon, you can kind of imagine, with the right process, you can produce the antiparticle version of it. But to tell you the truth, antibaryons are hard to produce. I know they have produced antiproton, and people have trapped antihydrogen. So you produce antihydrogen by combining antiproton with the positron. And I don't know if they've actually produced antineutron. I thought as high up as antihelium was produced, but I'm not 100% sure. Anyways, so these are some of the baryons that you have seen. You have seen the lambda baryon, one strange quark, And we talked about the omega baryon. That's sort of the beginning of the quark model, because the quark model comes from the success of, I learned how to pronounce his name. Gell-Mann, success of Gell-Mann in predicting existence of this particle and how to produce it. That's really the beginning of the quark model. So, so these are the baryons. I don't know what else to say about them. Proton is the lightest baryon, that's why it's stable. I guess that's everything. Did I forget anything? So that's the standard model. So let me just do a quick count of things that are in the standard model, just so that we recap. So there are 4 fundamental interactions. Of those, the standard model really covers 3 fundamental interactions, but 2 of them are unified as an electroweak interaction. So there's really 2 different types of interactions in the standard model. All right. So I guess that's kind of the end of the elegance of the standard model. And then the rest is, so there's, as I said, there are 24 elementary fermions, including the particle and the antiparticle. There's 4 plus 8 elementary bosons. So there's 32 elementary, let's not count the antiparticles because that's not actually fair. So not counting the antiparticles, there's 12, and I don't know if gluon goes down from 8 to 4 if I don't count antiparticles. No, let's just, there's at least 12 fermions. And with each of those fermions, with each of those elementary particles, you need to associate 3 parameters: spin, charge, mass. So, okay, let's say for spin and charge, you just leave them be because they are kind of discrete quantities. Spin half and charge of 0 or -1, or 2/3 or -1/3. So, okay, so leave them alone. But with each of these particles, you have their masses. So the masses are not determined by theory. They are experimentally measured. So you have 12 elementary parameters. Oh, wait, I'm almost out of time. Wow. So let me then tell you, I think I've talked about some of the modern tweaks already. Let's see. Okay, I'll just show them to you. And there's one thing that I haven't recapped, but I mentioned it last time. These generations of quarks, this is a kind of an oversimplification, because kind of distinction of something as up and down quark, it's according to the strong interaction. And the distinction of up and down quarks according to the weak interaction, they are not the same distinction. It's like having 2 different axes. They are rotated to each other. So I think the new poster might indicate that. So this is the newest version of that poster. It doesn't say, okay, it doesn't say skewed generations. But really, what these are quark flavors according to the strong interaction. And quark flavors according to weak interaction are different. And that difference is expressed in an angular parameter. So those are additional parameters. And you will see some of the things have changed. These used to be called electron, muon, and tau neutrino. Now they don't. They call it lightest neutrino, middle neutrino, and heaviest neutrino. And I think it's kind of explained here. So neutrinos, I'll just read it out loud, are produced in the sun, blah, 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 many other processes. Any produced neutrino can be described as one of the 3 flavor states, weak flavor states, electron, muon, or tau, labeled by type of the charged lepton associated with its production. Each is a defined quantum mixture of 3 definite mass neutrinos. So a way of saying is this: these are the weak interaction eigenstates, but they are not the energy eigenstates of neutrino. These are the actual energy eigenstates of neutrino, for which currently a lot of mass ranges are shown on the table, and further exploration, blah, blah, blah. The backstory here is, for those of you who want to look it up on your own, look up something called solar neutrino problem. It's a problem that was only settled around the early 2000s. And what the succinct description of that is, so these are produced in nuclear reactions. Our astrophysicists feel like they understand solar reaction well enough, so they estimate how many neutrinos from the sun we should detect. And when we build a detector and actually detect the neutrinos, with everything we know about them, we detect only a third as many neutrinos as we are to detect. And the solution to that is something called neutrino oscillation. The neutrinos that are originally produced as electron neutrino on the journey from sun to us, actually more from the core of the sun to the surface of the sun, turns into different flavors of neutrino. The detectors we have, originally they were only built to detect electron neutrino. So that accounts for the missing 2/3. If those electron neutrinos turned into these two other types of neutrino. And a way to make that mechanism work is to say neutrinos actually have mass, and there's 3 different masses, and these are, so that's what, I guess I am out of time. So neutrino, that's one modern tweak. In fact, that's the latest change to the standard model. And this is kind of an easy tweak. This almost actually matches up the skewed generations I was describing in the quark sector. So it kind of makes sense that lepton sector also has skewed generations. So I don't think a lot of people are troubled by that. They still don't show the C of quark-antiquark pairs, but that's fine. So this is produced after the Higgs boson was discovered. So it now has the measured mass, and it has the confirmed spin. It was, in theory, it has to be spin 0. Now we know it to be spin 0 from their measurements. I guess that's kind of it. That's the biggest thing. And I'm out of time to actually tell you why standard model cannot be the final theory. What's the best way to tell you in 1 minute? I think the best way to tell you in 1 minute is this phrase. You can search this on your own. So this is not something I will ever test you on. Search for physics beyond the standard model. It's an entire field of research. And the reason this is legitimate field of research is because every legitimate physicist thinks the standard model cannot be the final theory. And if you want to look at the listing of what's wrong with the standard model, you can look at, it is the first thing, problems with the standard model. And I will just tell you that this is the one that I thought most people found most convincing. And really this is the most unattractive thing about the standard model. That for a theory, fundamental theory of elementary interactions, there's like 2-3 dozen parameters. Well, okay, 1.5 dozen parameters. And it's when you have so many parameters, you can fit anything to match the observations. So a lot of people are uncomfortable with it. That's really why, at least that ought to be why there were people working on string theory, which has its own issues. It has more parameters than standard model. But so, I'll just leave that there.